Swayam Prabha. Digital India. Educated India.
Okay, dear students, so today again I will cover some level 3 biosensors, and this kind of technique also can be useful for multiplex detections. So level 3 detections and multiplex detection, these both are very much useful for point of care diagnosis, because from the multiplex detection we will get lots of information from a disease. So let's first complete all the level 3 part, then I will cover the multiplex part today. So today's main topic, that's why new detection systems that not only cover the level 3, also the multiplex diagnosis and their optimizations and then design. See, the main keywords for this today's topic in the multiplex sensor, point of care diagnosis, and definitely some level 3 part. So this part I just ended in the last class, that how we can use the level 3 detections for diagnosis. See, so in this case we use the electrochemical impedance spectroscopy, right? So first you have a bare gold surface where we use a thiolated antibody, because gold and thiol, they have a very strong interaction. So definitely your thiolated antibody can easily conjugate it on the sensor surface. This part can be easily done. They have very strong binding. Gold and thiol, they have very strong affinity. Then BSA, we just block the other part. Then we add a bacteria that is very much specific towards this antibody, and we got this sensor surface, right? And I showed you this all the images, and that I just wanted to again tell you that this is actually very useful for multiplex detection, this kind of sensor surface. And one part actually I am just now explaining. Here you can see one is the working electrode, one reference, one counter, right? This working electrode, this part we will immobilize for this S mutant detections, where we will immobilize all the antibody, and then we will add the bacteria. Then we will accordingly we will get the concentration of the unknown samples, and where we can detect how much S mutants present. Let's show you that part today. So here you can see in the left hand side in this image, see, first there is a 0. 0 means you have a sensor surface that you have antibody coated and BSA, right? This surface is ready for detection, right? This is the sensor surface that is called your background response or 0 signal. So that's 0. So you can see here is the this much we are getting. It's very low RCT value. We are getting very low impedance value. Now we are increasing the concentrations. See, the RCT value there, see, increases. RCT value increases, and this RCT value we are putting in the left hand side. This is the, what is this? Calibration. This is calibration curve. So I already told you how to get the 3 times standard deviations of the 0, and this is 3SD, and based on this we can detect the LOD, limit of detections, right? You can see, so we measure 3 times the each concentration, right? 1, 2, 3, 4, 5, 6, 7, 8, like different 8 concentrations we measure, and their error bar means this much standard deviation we are getting for each concentration, right? And we measure all the RCT value and we plot it. So y axis is the actual value of the RCT. Why we mention here corrected? Because we are actually just subtracted the 0 data. Suppose in a concentration value, so 0 data how much RCT, this much, and your concentration value this much. So your actual how much current, how much not here, not current, here you are getting RCT, mean impedance. So you are getting impedance because of this bacteria, actually how much? So you can subtract your 0 value. That's why we are mentioning here corrected value. So RCT value of your target and RCT of the 0. So if we minus it, then you will get the corrected, means actual amount of RCT that we plotted in the y axis, and x axis your all the concentrations of S mutant. Now, you can see one concentrations, generally what we are doing, we made the straight line and they can touch the intercept, this area is the limit of detection. But in this case, you can see these concentrations, if I remove it, you can see this concentration almost touched, right? It touched already the 3 times standard deviation value. That is why we can mention this is your limit of detections of this biosensor using electrochemical impedance spectroscopy. This is your LOD. This we calculated. So, like this way you can use this electrochemical impedance spectroscopy for your biosensor development. Now, suppose you have one sample, unknown sample, your unknown sample. You do not know how much concentrations of S mutants bacteria present. So, what you will do? Just this sample you can drop here and measure the impedance. So, how much impedance, suppose the corrected impedance value you are getting, suppose you are getting impedance this much. So, let us plot, so like this, still. So, this is your unknown concentration S mutant value. Suppose like this way we can calculate. See, now let us use this one for, as I showed you here, that one detection here we can go for the many other bacteria detection also at the same time, that is called multiplex detection. So, this is the single detection, and if you can use the all the sensor at the same time, then we can go for the multiplex detections. So, let us show you how we can design a multiplex sensor. So, here one basic example I showed you here. This is just a electrode we can pattern. For the multiplex biosensor design, you have to pattern your electrode. How you can pattern? Suppose this is a one ITO sheet. What is ITO sheet? It is generally it is we are taking a glass sheet and then it is coated of ITO nanomaterial. Then we are using the lithographic technique or sputtering technique, any one you can use, and we can pattern the surface. Suppose you will have the one working electrode here and another working electrode here. You can pattern, and one here you have to use one reference electrode, one counter electrode. So, one is working 1, another is working 2, another is reference, another is counter. So, the reference counter is the common. So, you can use common reference counter for these two, and there should be connector, right? There should be the connector. Now, see, if I2 is everywhere, so everything can be connected each other. So, you have to remove the I2, right? That is why you need the pattern. You have to remove the I2. Only this thing will be connected. This working electrode, this reference, the counter, you have the connections. Here you have connections. Then you can use a adapter, and that can be connected to your potentiostat. So, this is the example here. You can see here. So, one is the working 1, another is the working 2, another is the counter and the reference. So, how you can use this one for the multiplex sensor now? In the working 1, you can use one very specific antibody that can be useful for one analyte detection, and working 2 you can use another antibody for another analyte. Suppose in working 1 you are using malaria, malaria antibody detection, okay, and working 2 suppose you are using dengue detection. So, here you will use the antibody for malaria, and here working 2 you will use the antibody for dengue. Now, your counter and reference, they will be free and they will be the common electrodes. Also, we can use like working 1 case separate counter electrode and working 2 case separate counter electrode, but this is another design. But here we are using the common counter, common reference. That's possible, this kind of design. Now, you can go for the sensor development. Then see, on this you can, this is the target, right? This is the malaria and this is the suppose dengue. So, if your solution, your sample solution contain malaria and dengue both together, then both they will bind. But if you don't have, like if your sample contain only malaria, don't have dengue, then only this part will bind and here dengue part will not bind. So, when you use a secondary antibody with some level, then the secondary antibody will bind only the working one, and secondary antibody with label that will not bind in the working 2, because you don't have dengue. That's why accordingly you will get the signal. When you will get the electrochemical signal from working 1, you will get the high signal. From working 2, you will not get the signal if you don't have dengue. Suppose in this monsoon region, if some patient come with the fever, we may think this is for malaria, this is for dengue or something else. So if we use this chip, then we can easily predict this is for malaria or dengue, right? So something like this. So we may have a full information that how we can go for the treatment. This is very important. That's a multiplex sensor. We will have a complete information. Also, maybe this disease may be something other, bacterial maybe infection, something like this. So then we can go for the another. Here we use actually 2 target. We can go for 3 target if it is for bacteria or something virus related. That also we can detect. So accordingly, you can see the signal difference. If you have the disease, then you will get the higher signal. Because we are using the sandwich with secondary antibody that conjugate the level, we will get the higher signal. If we don't have, then we will get the lower signal. Then accordingly we can predict that if it contain the this your target or not. This is very much useful. Now the most another important part I will show you, the design of the device. You can see that I showed you the blood drop and then some plastic case, some membrane. Why we need for this, for multiplex whole device design? So that is the device design part. That part also I want to teach you. So sensor part done, right? That way we can design a sensor. Now we are coming the next important stage is the device design. So generally, as I mentioned, before going to the detections, we are collecting the blood sample and then we are going for processing. Many pre-processings we need, right? Maybe we have to go for the in the centrifuge. We can separate the blood cells. We can collect the serum or plasma. Then we are detecting. So these steps we may need some advanced laboratory facility. We need some expert persons also. That also we can avoid if we can use some design of some new technique on the device. Let's show you. See, here we use the whole blood sample, but you know the blood samples contain many blood cells, like red blood cell, white blood cell. So those cells we have to remove them. So we can use here a membrane that is called blood cell separation membrane or vivid plasma separation membrane, that is commercially available, vivid plasma separation membrane. Those membrane, what they will do, they will separate the blood cells. Then basically you will get only the plasma. This plasma now will go through your membrane. Why we need some other membrane? In this membrane we can use some chemicals. Sometimes we need for electrochemical, chemical redox cycling, we may need the ruthenium chemical, right? Or maybe we need the T-shape, we may need the potassium ferrocyanide. Those chemicals we can put on a membrane, right? In that solution, chemical solution we can put. Then we can go for drying. That is lyophilized conditions we can make. That lyophilized membrane we can keep just top of the sensor. So your sensor surface basically will be like your antibody coated. Here BSA, this is antibody coated, and on that surface you will have the membrane. This kind of membrane we can use. You can use one membrane or another membrane also. So one membrane we can use for chemicals, another membrane maybe we can use for secondary antibody that conjugated with some tag, that you can use for another membrane. Now when you drop these samples, then all the blood cells will be separated, you will get the plasma, and this plasma will go through this membrane, it will dissolve the chemical, then and your target also will come to the surface, they will bind, and your secondary antibody that conjugated with the label, that also will bind on the sensor surface, and accordingly we will measure the electrochemical signal. Like this signal difference we will get. So it actually looks like this. This is a plastic case we used, so to prevent some damage, and on this below this plastic case we can use some membrane that contain all the reagent. Then we will drop the sample, and this connection will connect to your portable potentiostat, and we will see the data, like this kind of data we can see on your skin. So, this is the two target potentiostat we can design, and sometimes we need the multiple target like 4. Accordingly we can design the potentiostat that can help you detect the all the signal. So, if you go like next one, like if you have the 4 target, how we can design. So, accordingly you can design, see here, like working 1, working 2, working 3, working 4. So, 4 working electrode, and they have one common counter electrode and common reference electrode. Okay. So, working 1, you can see, suppose you want to detect like malaria, dengue. One is that sometimes these infections also we want to detect, very much important in this Indian scenario. This kind of infection is a tuberculosis bacteria and HIV. So, these 4 analytes sometimes we need to detect at the all together, tuberculosis, HIV, malaria and dengue together. So, then we can design a multiplex sensor. So, one sensor can detect malaria, one sensor can detect dengue, another one can detect tuberculosis, and can detect the HIV. And specific, we are using all the specific antibodies, and when you draw some blood cells, some blood samples, then blood cells will be separated, and then see, this is the vivid plasma separation membrane that is separating your blood cells. Then you have some membrane, some hydrophilic membrane. There you can put your all the chemicals, your secondary antibody, these things. Then those will come on the sensor surface, and you will get the signal change if it contains malaria, dengue, tuberculosis, HIV. And if it contains only one, then you will get the signal change for only one. Other cases no change, only background signal we will see. Okay. So, it will see your multiplex chip actually like this. See, very simple, just your dropping, and if you have the target, and that can be detected with separated region. See, after adding the blood, I am adding on sometime the PBS, some buffer also. Maybe sometimes you may be provided a extra tube that may contain a buffer. Why? Maybe you are adding, just after pricking your finger, maybe you are not getting enough blood, right? So, just few, like 1 drop of blood, and when you are adding 1 drop of blood, suppose it may not penetrate all the membrane. So, you need more samples. Then you can add some buffer so that this blood can, this mass volume, suppose you have like few microliter, that can be sufficient to go to reach this all the 4 electrodes. That is why we may need some time to add the buffer, more solution we may need. So, you can add some PBS buffer, that is why. So, this is the design for 4 target detections. Now, let us see how we can detect the 4 target using a unknown sample. Suppose I provided unknown sample. Suppose I took some, means I can prick your finger, or maybe I can collect some blood, and from this, suppose I took like 2 ml blood sample. Then I have to collect in this blood sample if I have these 4 analyte present or not. So, what I will do, this blood, so from here few microliter, around I can take 50 microliter. I can drop here. If I need PBS, then I can use some PBS buffer also, if it is not enough. So, in the 4 working cases, I may get the signal change. So, number 1, suppose I am using the chronocoulometry. I am getting the signal number 1, and number 1 case you should know the background current. So, this is the background, and you are getting the signal 1 1. So, this is like charge versus time. Second case, working 2 also, like charge versus time you are plotting. This is your background 2 and signal 2. And third case also you have to predict, you should know the background 3 and signal 3, right. And 4 case also, 4 case also you have to predict, like background 4 and signal 4. Okay. So, this all the information we will get. Now, we have to make the calibration curve. This all the 4 cases, I have to make the calibration curve. So, let us get the 4 calibrations. So, 4 calibrations we will get. Suppose, so number first cases, suppose you are getting the calibration. So, you can now plot the charge versus concentrations. Means before going to the unknown concentration, so first you have to check with the known concentration, with the different you can change, you can vary the concentration of the like malaria, dengue and HIV, tuberculosis, that all the things you have to measure in some known concentration. Then you should plot 1, 2, 3, 4 calibrations. So, you will get the 4 calibration, right. Like 4 calibration you got it with known. Now, from unknown, how much you will get some current. Here you are using chronocoulometry, you will get the output is the charge. So, from the no case you can how much charge you are getting, number 1. So, number 2 case how much you are getting, number 3 case how much you are getting. So, that you can easily predict, right. So, this much current equivalent to this much concentration. So, we can use the algorithm sum, means all the things definitely we will not do the manually. We can use some algorithm, some automatic in our electronic device. So, if from an unknown sample in the working electrode 1, if you get this much current, it corresponds to this much malaria. So, on your screen, detector screen on your mobile phone, if it is connected, on your screen you will get 1, 2, 3, 4. So, 4 value only we can see. Maybe other, if they do not have target, you will see the 0. Other cases maybe this much picogram per ml or 10 picogram or 100 picogram per ml. This much value will show you only. So, these all the measurement, these things we can do before commercialization of this kind of the device, right. So, then we can use the mathematical algorithm, these things they can do it automatically, this all the calculations. So, that is why it will be pretty easier and user friendly. So, anyone can use, no need to go no need to understand all the basic mechanism of the sensor. They can drop and sense. They drop this blood samples and they can see the digital value on the screen. That is the concept we will use for this development of the multiplex sensor. Now, let us show you another example of the multiplex sensor. Sometime doctor suggests to check the glucose, lactate and uric acid all together. So, they do not need the antibody base, but we need some enzyme based sensors also we can develop. So, glucose case specific enzyme we can use, lactate case and uric acid case. So, that specific enzyme we can immobilize on the sensor surface. Now, if you drop your sample here and accordingly if you want to get glucose, then very specifically glucose only here will oxidize, lactate case only lactate will oxidize, here glucose will not oxidize because they are very much specific, uric acid. So, then we can get the 3 curves and accordingly. So, if you have glucose, you do not have much lactate and uric acid. So, you will get only the glucose signal, but other cases you will get the low signal, something like this. Okay. So, this multiplex sensor, that is why will be very much useful. Just in a single go you can get all the information at the same time. Just maybe here if it is waiting time only 5 minutes for your data measurement. So, within a 5 minute 1, 2, 3 value means glucose, lactate and uric acid, all the data you will have and you can go for the now treatment. That is the utility for the multiplex sensor. Okay. Now, let us show you some other design of the multiplex sensor. So, that I taught you up to now, here it is a very generic, very basic concept. So, you have to understand that this kind of concept can be useful for any kind of disease detections and we can go for the different design, depends on your need. See, sometimes you may need design something like this way, like here you can use the working 1, working 2, working 3, even working 4, working 5, working 6, like many target you can detect at the same time. and one common reference electrode, one common counter electrode. So, its design can be like this also. See here, and this region will be your testing region. Just you can drop the your sample here, and you may get your unknown concentrations of the target. How many target you can go for detection? Let's see, 1, 2, 3, 4, 5, 6. At the same time, you can go for 6 detections also. It's possible and very easily. And see, it's very miniaturized, very small. The sample, the platform size. So your sample volume also will be very, very small. Definitely, as your sample volume, because it is very small size. So maybe sometimes 10 microliter will be fine for this. Okay, this is enough. Then we don't need too much sample volume. Again, so this one I taught you. See here 1, 2, 3, 4. So 4 target at the same time you can go for detections. Another thing, it is commercially available one, gold chip. So sometimes we may see here we are sharing the counter electrode and reference electrode. Sometimes you may if you feel that let's use the single for each working electrode, let's use the independent reference and counter electrode. See here, this is the design, like one working, one reference, one counter. See 1, 2, 3, 4, 5, 6, 7, 8. So and opposite side also. So 16 target at the same time we can detect. See here actually we use some paper based membrane. See and we use a plastic case and some paper we can use. There we can drop on a paper, you can drop your chemical and you can go for the lyophilized conditions. You can put on the top of the sensor surface and then just drop your blood, and your blood cells all will be on the upper part of the sensor, and at the bottom you will get only the plasma, and you can detect all the marker. See, like this way many target you can detect and you can design based on your needs. That's why this multiplex detection sometimes is very useful for the doctors who want to decide that which way they should go for the treatment. That's one example I told. If some patient come with some fever, is it for what? Nowadays maybe we have to check for the like SARS-CoV-2 also, some virus, like one sensor chip should contain a SARS-CoV-2, and another one maybe some like dengue. This in time maybe dengue also can be a cause for the fever, or another maybe for the malaria, and another maybe some other bacterial detections we can go, and we can take the decision this fever due to what, and we can go for exact means appropriate treatment. If it is for viral, but if we go for the antibiotic treatment, is not useful, and this is very, very dangerous also for the patients, because it can also increase the resistance for this antibiotic on patient. So that's why it is not good idea to give the antibiotics immediately after going for this multiplex testing. Only we can go for the treatment. That will be very much useful. That's why. Okay, so the conclusion for this today's teaching, that multiplex technique is the very much useful to get the complete information about a patient, and we can go for the proper treatment. Thank you for this lecture today, and next lecture I will teach you again some more advanced technique of the multiplex sensor and for point of care diagnosis, how we can use this technique. Thank you very much.